Okay, yesterday we talked about Boyle's Law, which was the first of the minor gas laws. Remember, a minor gas law relates two of our four gas law variables. So we allow two things to change so we can see what the relationship is between those two things, and then we hold the other two things constant so that those are not changing. We're doing another minor gas law today, and that is Charles' Law. Again, named after Mr. Charles. 1787 or circa 1787 is about when he came up with this idea. This minor gas law is the relationship between volume and temperature. So those are the two things that we will allow to change, which means that we are not changing pressure or amount. You might have some experience with this relationship already. If you have, for example, purchased helium balloons in the winter. Anybody done that? Take them outside and what happens to them? They shrink. And then you bring them back inside and they expand. They look fine again. That's a change in temperature between going outside and inside. That changes the volume of the gas, which makes it look like the balloon's deflating and inflating. But none of the helium came out, so you're not actually changing the amount of gas, it just makes it take up less space and then more space. So, you already know this relationship. If temperature increases, then volume increases. And if temperature decreases, then volume decreases. We call this a direct relationship because these two things change together. They both go up or they both go down. Yesterday when we did Boyle's Law, we would have called that an inverse relationship because one thing goes up while the other goes down. So yesterday we had an inverse relationship. Today we have a direct relationship. Why does that happen? Why does the volume change if the temperature changes? What happens to your helium balloons when you take them outside? Do you know?
I think so.
Okay.
Particles speed up really fast when they get cold.
You're almost right. Particles speed up when they get hot. So then they move more, which would make the volume bigger, if your container is free to expand. That's pretty much exactly it. An increased temperature means increased velocities or increased motion of your molecules. If you increase the motion of the molecules, you would increase the number of collisions between them, also collisions with the container. So if the container is free to expand, like a balloon or something that stretches, then those walls of the container will be pushed further away, and the volume will get bigger. This also has to do with something that you're not supposed to do, possibly with aerosol cans and a campfire. What happens if you do that even though you're not supposed to? If you throw the aerosol can in the campfire, eventually it explodes. If you increase the temperature of the gas inside the can enough, in a rigid container like that can, that container can't expand and contract like a balloon. So eventually, you'll get enough of a buildup inside, the can will explode. So if you increase the temperature, you increase the speed of the molecules, you increase the collisions. If the walls are free to move, the volume will increase. We could also go through the opposite situation. If you decrease the temperature, then you would decrease the velocities. You would decrease the speeds and the collisions. And if the walls are free to move, the volume will decrease. This is just like the helium balloons. When you take them outside on a cold day, you decrease the temperature. The helium atoms move slower. They move less. The walls of the container are free to move, so it looks like your balloon is shrinking. Now that we understand the relationship, next we'll have the equation. Yesterday we had an inverse relationship, and the equation had two things being multiplied. P1 times V1, P2 times V2. This time we have a direct relationship. So what's our equation going to look like? Instead of multiplying, what's the opposite of multiplying? Dividing. So this time our equation is divided. Volume 1 divided by temperature 1, and volume 2 divided by temperature 2. We still have the before case and the after case. The 1s are before the change, the 2s are after the change. We have one little note that goes along with this equation, and that is that your temperatures have to be in Kelvin before you put them into the equation. So you have to do just a little bit of temperature conversion before you start. All of our thermometers that we have measure in Celsius, so all of your story problems will give you temperatures in Celsius, or almost all of them will. You have to convert Celsius to Kelvin before you put your numbers in the equation. If you don't remember how to do that, you could look back on the chart we filled in the other day. K equals C plus 273. K equals C plus 273. It's pretty easy. There's not a lot of math to convert Celsius to Kelvin and vice versa. But you have to remember to do it before you put the numbers in the equation. So remember, K equals C plus 273. So let's do some examples. If a 45 milliliter sample of gas at 26.5 degrees C is heated to 55.2 degrees C, what is the new volume of the gas sample? Just like yesterday, if you're not sure where to start, make yourself a list of what you have and what you're looking for. What's the 45? Volume, 1 or 2? First one. What's the 26 and a half? First temperature, 55.2. Second temperature, what are we looking for? Second volume. Okay, so first volume, first temperature, remember we need to convert that to Kelvin. So add 273 to 99.5. Second temperature, add 273, 328.2, and we're looking for volume 2. Once you get your temperature conversions done, then you can plug the numbers into the equation. Again, on a test or a quiz, this is the minimum amount of work that I need to see. I need to see this step right here where your numbers go in. Where did you put your numbers? Cross multiply and divide, right? Just like you would do for a math problem. Cross multiply and divide. Check for sig figs. Go back to the numbers in the question. We're going to take the easy way with sig figs on these. Go back to the numbers in the question. Based on the numbers in the question, how many sig figs should we have? 3. So you should get 49.3 if you do your math right. One little side note on the sig figs on this, by going back to the numbers in the question, we're not technically following the rules because we did that little conversion step in the middle where we added, and we didn't worry about sig figs when we added. But rather than make you do that, it makes things a little bit more complicated as you go through the math. We're just going to take the easy way out on this one. Go back to the numbers in the question, base your sig figs off of that. It's not technically right, but we'll cheat a little bit on this one. Ready for the next example? Next one. If a sample of gas occupies 25 liters at 0 degrees C, what temperature in Celsius must it be to occupy twice that amount of space, or 50 liters? What's the 25? Okay, so 25 is the volume, 0 plus 273 is the temperature. We're looking for temperature 2, and what's volume 2? 50. So again, make your list if you need to. Notice that the temperature was asked for in Celsius. So what will we have to do when we're all done? Subtract 273. It is standard practice to return your answer in the units you were given. So if you are given Celsius, standard practice is to return your answer in Celsius. And again, once you get to this point, plug in your numbers. Cross multiply and divide. Watch out for the ones where the variable is on the bottom. Sometimes this causes students trouble with their algebra. So be careful when the variable's on the bottom. If you cross multiply, it shouldn't be an issue. Go back to the sig figs in the question. There were 3. Temperature comes out as 546 K. And then subtract 273. Final answer comes out to be 273. Celsius this time, not Kelvin.